Good morning, class. Hope you are all well. Today we will discuss about the uh, next part of the previously in our previous class we discussed about the ripple marks. Firstly, we discussed about the bedding. Then we discuss about the ripple marks. Mainly, we discuss about the different morphological uh, points or morphological features within the ripple marks, such as the brink point, crest point, trough point, stoss side, lee side, the ripple wavelength, amplitude. Um, what are those points or those areas of a ripple? Now, this is the link of the previous class. So, if anyone try to follow the previous class, and they can go through this YouTube link and follow the previous class. Now, mm, in transverse section uh, of a ripple marks, the ripple mark can be symmetrical or they can be asymmetrical. That depends whether the length of the stoss side is equal or not equal to the length of the lee side. It is always the stoss side is either greater than the length of the lee side or equals to the length of the lee side. Stoss side will never be less than in length with respect to the lee side. So either stoss side is greater than lee side or equals to the lee side length. Now, depending on this symmetrical property, the ripple marks can be divided into two groups. One is the asymmetrical ripple mark, in which the stoss side length is greater than lee side length. So in the left hand figure, you can see that here this is the stoss side length. It is greater than the lee side length, and also in this case, the inclination or the dip of the stoss side is generally gentle compared to the inclination or dip of the lee side. So the lee side is basically steeper than the stoss side, and this kind of asymmetrical ripple marks will form from a unidirectional flow, or we call them as current. That is why they are also known as current ripples. So this kind of asymmetrical ripples or current ripple marks, they are indicative of a directional flow, unidirectional flow or current, and the current is moving from stoss side to lee side. So they are very good indicators of flow direction. In contrast, the symmetrical ripple marks, where the length of the stoss side and the length of the lee side is almost equal, although in nature there are some variations are also there, but generally it is considered that in case of symmetrical ripple marks, the length of the stoss side, you can also see in the right hand picture that this length is almost equals to the this length. So these two lengths, that is the stoss side length and lee side length, are almost equal to each other, and thereby the inclination of these two sides are also nearly same. So these kinds of ripple are almost symmetric, or a mirror image. One side is almost a mirror image to the other side. So that is why these kinds of ripples are called symmetrical ripple, and these kinds of ripples are formed by bidirectional oscillation flow. Oscillation means back and forth movement, back and forth movement. This kind of movement is known as oscillation movement. So this kind of ripples in old literature, you can find that these kinds of ripples are also called as oscillation ripples. Nowadays the oscillation ripple term is a little bit obsolete, so nowadays it is known as symmetrical ripple or wave ripple. And the distinguishing thing of this symmetrical ripple or wave ripple from the current ripple is that in wave ripple, firstly the two sides, toss sides and lee sides, are equal in length, that is symmetric. Also, in wave ripples, the crests are more sharply pointed than the trough regions. You can see here that these trough regions are broadly rounded, whereas the crest regions are sharply pointed. That is why you can clearly identify the crest lines, that is the line joining the successive crest points. This is very sharp, very angular. So these sharply angular crest points, in contrast to the broadly rounded troughs, this angular crest point indicates the stratigraphic top direction. That means the way up side of a stratigraphic succession. So the two types of ripple marks, asymmetrical and symmetrical ripple marks, they are used for two different purposes. The asymmetrical ripple marks are used for indicating the flow direction, and the symmetrical ripple marks are used for indicating the stratigraphic top bottom direction. Now in the previous slide you show the picture of both symmetrical and asymmetrical ripple from the top view. So that is the top view where you can see only the uh, trough and crest lines. Now in this picture you can see the transverse section of those asymmetrical and symmetrical ripples. So you can clearly see that in transverse section of an asymmetrical ripple, the toss side length is greater than the lee side length, and the inclination of toss side is gentle, whereas the inclination of lee side is steeper compared to the toss side inclination. So flow direction is from toss to lee, that is in this figure from left to right. In oscillation ripple, where the movement of current is back and forth, there you find this kind of symmetrical ripple in which the toss side length and lee side length are equal in length as well as equal in inclination angle. And in this type of ripple, the trough regions are broadly rounded, whereas the crest portions are sharply angular, and this sharply angular crest indicates my stratigraphic top direction. Now in formation of any type of ripple marks, whether it is current ripple or wave ripple, two types of sediments are important during their formation. The first type is the sediments which move as bed load or saltation, that is sediments with contact with the bottom substrate, either continuously along its transportation path, or occasionally came in contact with the substrate. And the second type of sediments which move by suspension. So during the formation of any kinds of ripples, these two components or two types of sediments, that is the sediments move in contact with the substrate and sediments are completely in suspension, they contribute or they deposited in different parts of these ripple marks and ultimately resulted the sedimentary structure what we found in the rock record. Now, previously we taught about the divisions or different types of ripple marks depending upon the crest line morphology. So basically this is the top view. From top view you can only see these crest lines. So we observe that different types of crest lines are there. Some are straight crested, some are sinus, some are catenary or cuspate, two linguoid and lunate types. Now, depending upon this crest line morphology, ripples are of either two-dimensional when the crest lines are straight. That means when these crest lines are straight, we call them as two-dimensional ripples or ripple marks. And when the crest lines are sinus to catenary, cuspate, lunate, or linguate, we call those ripples as three-dimensional ripple marks. Now, if we plot the flow energy condition, that is the flow velocity, with respect to the crystalline morphology of ripples, we can clearly see that with increasing flow energy, with increasing flow velocity, the crest lines of any ripple marks is gradually changing. Initially it is straight lined, then with increasing velocity or with increasing flow energy, the crest lines become sinus, then catenary or cuspate to lunate or linguate. So these kinds of sequential change in crystalline morphology is clearly indicating that the flow velocity or flow energy is gradually increasing. So this differential crystalline morphology from the top view, they will tell at a glance about a relative flow energy condition of the medium. So if you found that the crest lines are straight crested, straight, you can say that the flow energy condition is low. When you find sinus or catenary or cuspate uh, crested ripples, you can say the flow energy condition is medium. And when you can find isolated lunate or linguate types, you can say that the flow energy condition is high. Now, often you heard a similar terminology like ripple that is called dunes. Similar forms like the ripple marks, but larger in dimension. So basically ripple marks are all millimeter to few millimeters to few centimeters in dimension. In contrast, the dunes are in meter scale. That is the length, uh, wavelength, altitude are in meter scale. So it is the larger version of ripples. So similarly, dunes are formed by the same way as ripples are formed, and dunes also show this type of almost these types of um, crystalline morphological variations, but the names are a little bit different. That I come in my later slides. Now, if we plot the changing bed forms, that means with a directional flow, how the sediments transported and formed particular sedimentary structures. If we plot those bed forms with increasing flow strength, flow energy for a unidirectional flow, we can get these kinds of structures. So in experimental study, people found that these structures are changed in a predictable sequence depending on the uh, change in flow velocity, depending on the change in grain size of the sediments, and also the depth of the flow. Basically, any sedimentary structures, not only these sedimentary structures, but any sedimentary structures are best formed in a non-cohesive sediments, particularly for a medium grained sands in which the diameter is almost 0.6 to 0.7 millimeter. In this figure also, you can find that the uh, features are best developed with medium grain sand having diameter of 0.7 millimeter, and more finer sediments of this size, they becomes cohesive, and because of this cohesiveness nature, it is very hard to dislodge the sediments from its resting position and transport them, and finally forming different kinds of sedimentary structures. So for a cohesive sediments, erosion and transportation is very hard. So that is why the non-cohesive sediments, particularly the medium grain sands, the primary sedimentary structures are best developed. Now, first, the sediments are in static position. That is, they are not moving through the flow. That means the energy condition is not sufficient to dislodge the sediments from its original position. Now, with increasing flow velocity or flow energy condition, the sediment starts moving, and fastly they formed some plain laminations with very less amount of flow energy condition. These are known as plain lamination or plain blades of lower flow region. With increasing velocity or with increasing flow strength, then form the small ripples, and these ripples are in dimension of few centimeters, and the spacing between these ripples, that means the distance between two successive ripples, is almost 10 to 20 centimeter. As flow velocity increases, you can see in this picture that flow velocity is increasing from top to bottom. So as flow velocity increases, these ripples enlarge in size, enlarge in dimension. So from ripples, it will enlarge in size and form sand waves. These sand waves, again with increasing energy, form dunes. So you can see that the basic structure of ripples, sand waves, and dunes are same. They have a stoss side and a lee side. The stoss side is gently dipping, whereas the lee side is steeply dipping. And you can see some internal laminations. Uh, these laminations are all found in the sand waves, ripples, and in dunes also. And these internal laminations are inclined towards the flow direction. So this basic structure is same for ripples, sand waves, and dunes. Only difference between these three primary sedimentary structures is the dimension. So sand waves are larger in dimension than ripples. Dunes are far larger in dimension than sand waves. So with increasing energy condition in the lower flow regime, that means when the fluid value or fluid number is less than 1, at this condition, with increasing energy starting from the plane lamination to ripple marks to sand waves to dunes. Now with further increasing of flow velocity or flow energy, the fluid number then crossed the value of 1. That means fluid number becomes equals or greater than 1. Now at these conditions, the previously formed dunes in the lower flow regime, that is in the fluid number less than 1, that condition dunes, these structures are destroyed, and at fluid number greater than 1, again some plain lamination or flat beds are formed after destroying the dune structure. So these previously formed dune structures, which is formed fluid number less than 1, with increasing velocity, when fluid number becomes greater than 1, these dunes are destroyed and formed these plane laminations or plane blades, and that plane lamination is occurred in the upper flow regime. Now with further uh, increasing the energy condition or flow velocity from these plane laminations, some dune line structures formed. These dune like structures are look same like the lower flow regime, but the difference is this structure, these dune like structures in the upper flow regime, in external morphology they look same, but when you observe the internal morphology, you can clearly see that in the upper flow regime dune like structures, there the internal lamines are inclined towards upcurrent direction. In this picture, my flow direction is from left to right. In lower flow regime dunes, the internal lamines are inclined towards the flow direction, but in upper flow regime antidunes, that is the dune line structure what I previously told, they are known as basically antidunes. These antidunes are looks like dunes, but the internal lamines are inclined towards the upcurrent direction. So this is my upcurrent direction and this is my down current direction. That means the flow going to this direction is down current. So the internal lamines in antidunes are inclined towards up direction. That is the difference of identification between dune and antidune. Otherwise the dimension and the external morphology are almost same. The spacing between the two successive antidunes is almost 5 meter. Now if we summarize the entire flow regime concept with respect to flow velocity, flow energy, and sediment grain size, here scientists plot the sedimentary structures with respect to flow velocity in the y-axis and sediment size in the x-axis. So you can see that the grain size is increasing from left to right. So in the higher grain sized, in the lower flow region there will be no movement as the weight of the material, weight of the sediments is sufficiently high, so with minimum energy with lower flow in the lower flow region, grains are not in movement. With increasing energy condition, with increasing flow velocity, some plane laminations are formed, then form the dunes, and after that, when fluid number becomes greater than 1, then for very minute portions, some plane laminations are formed and then form the antidunes. So there is, for larger grain size, there is no ripple marks formed. As I previously told you that with changing velocity, people find that the sedimentary structures formed is a function of sedimentary grain size also. Not only the sedimentary structures formed is not only a function of the flow velocity, but it is also a function of the sedimentary size. So for the higher sedimentary size of sand, you can see that starting from the region of no movement to plane laminations of lower flow region to dunes, then when fluid number exceeds the value of 1, form the antidunes. But for grain size in or whose diameter is below sand size, or more precisely medium grain sand, that is the diameter is almost 0.6 or 0.7 millimeter, there first there will be a region of no movement, that's a very thin region, then a very thin region of plane laminations, and after these two thin regions immediately the ripples are formed. So there is a vast field of ripple marks, then it goes to dunes, then with increasing velocity forms the upper plane bed, and when the fluid number exceeds 1, it forms antidunes. So you can see that below the sand size, particularly for the medium grain sand, particularly for this region's sands, with increasing velocity, you can intersect all the 4 major primary sedimentary structures formed with changing velocity. Firstly, in lower flow regime, it is formed ripples, then goes to dunes, then the upper plane beds, and lastly the antidunes. So all the structures are best developed for medium grain sand, and obviously when the velocity is very low, then some plane laminations are also formed, but their region, their vertical extension is very low, so that is why it is not shown in this graph. So starting with very thin region of plane laminations, then ripples, then dunes, upper plane laminations of upper flow region, and then antidunes. So all the 5 primary sedimentary structures are observed from medium grain sand. The size below this medium grain sand or above this sediment grade, this sediment size, there you will not find all these 5 types of structures. As you can clearly understand that the file the grain size below the medium grain sand is the fine sand and then silt and clay, so the cohesiveness property is increasing with decreasing grain size, so it becomes very difficult to erode those finer grain sediments. And in the upper size class, as they are of higher weight and specific gravity, it is also very difficult to move them due to their higher weight compared to the flow velocity. So there is a huge field of no movement of sedimentary grains. So only the medium grain sand, the primary sedimentary structures, of like the plane laminations of lower and upper flow regime, ripples, dunes, antidunes, they are best developed. Now, like the ripples, dunes are also have different morphologies, and these different types of dunes are named depending upon the crest-line morphology. So you can see in the first picture, these are known as transverse dune, where the crest lines are almost U-shaped, but the opening of this U is towards the flow direction. That is, it is formed for a unidirectional flow, and all the crest lines are mutually connected to each other. So it is basically a larger version of um, your catenary or cascade ripples. The crest lines are interconnected with each other. Crest lines are U-shaped, and the opening of U shape is towards the flow direction, towards the bottom current direction. When these transverse ripples they are detached from each other, that is those U become isolated, then they formed the Barkhan dunes. That means here the U's are isolated with each other, they are not connected with each other. Again, the opening of U is towards the down current direction, or otherwise you can say the closer of U towards the up current direction, the closer of U, or you can say the horns of the U, that is these pointed tips, they occur towards the down current directions. Now, both the transverse and Barkhan dunes are formed due to unidirectional flow. In the same way, another isolated U-shaped dunes formed, those are known as parabolic dunes. Here, this is also formed in unidirectional flow, but here the opening of U is towards the up current direction, that is opposite of Barkhan dunes. And these kinds of dunes are mostly observed near the coastal areas. So these are parabolic dunes. Now, when the flow conditions is varied, in all those transverse, Barkhan, and parabolic, the flow direction is uniform, that is one directional. But when there is more than one directional flow, then the morphology of the dune crest lines varies. Firstly, when the flow direction is from two sides and the angle between this flow is almost 10 to 15 degree, then with coalescence of these two flows, they formed a long ridged dunes fields. So these two flow collide with each other and formed a linear ridge. This linear shaped ridged dunes are known as sieve dunes. The name sieve dunes is came from the Arabic word. In uh, Arabian countries, the Arabian swords are such straight fashion. So from those sword shapes, these kinds of dunes are named as sieve dunes. You can also call them as linear dunes. And lastly, when the flow directions are multidirectional, that means it is not restricted to a particular direction. So in this picture, the flow direction is comes from here, it is from here, it's from here, and it's from here. So when the flow is multidirectional, then With coalescence of these multidirectional flow, they form some star-shaped dunes. That is, a dune having differently oriented crystlines. So in these dunes, you can see that this one is one crystalline, this is one crystalline, this one is one crystalline, this one, and this one. So all these crystlines are formed during differential directional flow, and these directional flow form some dune crest, and these dune crests are ultimately collided in a point, and now it looks that from that point the crystlines are radiated in different directions, so they looks like a star. That is why these dunes are known as star dunes. Now in ripples also, these kinds of multidirectional crystalline orientations are observed, and those are called interference ripples. So you can see in the right hand picture that this one is one crystalline, this is the crystalline orientation of another set, and this is the crystalline orientation of another set. So you can see that at least three crystalline orientations are observed here. So these three crystallines are formed due to different directional flows, and now they are interfere with each other. So that is why these are called interference ripples, and these kinds of interference ripples are very common in the tidal flat regions. That means the regions where tidal activity is more pronounced, is more uh, well observed. Those areas are known as tidal flats. So these interference ripples are very good indication of tidal flat region. So in the right hand picture, this picture is of from a present day tidal flat of Odisha, and these kinds of multi-directional crystalline oriented ripples or interference ripples are also found in rock record also. So definitely these kinds of interference ripples indicate that in ancient environment here exists an tidal flat region where multidirectional flow is occurring, and that is why this kind of differentially directed uh, crystlines of ripple marks is formed. So in this picture you can see that this one is one crest orientation, this one is the one crystalline orientation, and this one is the one crystalline orientation. So at least three crystalline orientations are observed. So that is why these are called interference ripple, and they are found mostly in the tidal flat regions. Now another kinds of ripple, that is the rhombic ripple, or often people call it as rhomboid ripple. These ripples are generally formed in aqueous condition, and they are the current ripple marks. They are characterized by reticular arrangement of some diamond shaped tongues, and each tongue have two acute angles, this one and this one, each tongue having two acute angles, one acute angle pointing the upcurrent direction and another acute angle pointing the downcurrent direction. So from these kinds of rhomb shaped ripples or rhombic ripples, you can say the sense of the flow, that is either flow is from left to right or from right to left, but exact flow direction is hard to say from these kinds of ripples. Why I am telling that, you can say the sense of flow, that is your flow direction is now limited with respect to every possible direction. So either your flow is from left to right or from right to left, but it is never from this side to this side, from top to bottom or bottom to top. So either it is from west to east or east to west, but not from north to south or south to north. That is, the acute angles determine the or indicating the up current or down current directions. And these kinds of ripples are formed when the water depth is very narrow, is very low, shallow water depth condition. Generally it formed in the beaches and particularly in the seaward side. And these kinds of ripples are easily identified in the rock record also by their uh, striking pattern. It looks like the fish scale. So on the basis of that scale like pattern, people identify these kinds of ripples and they can interpret about the sense of flow from these kinds of ripples. Now these ripples are often migrated from one point to another. That is, migrated means forwardly moved. So the ripple marks once formed, they are not static in their position. Now previously I told you that for formation of ripple marks there are two components or two types of sediments are included for formation of ripple marks. The first component, that is the particles in contact with the substrate, and there are some particles which are suspended in the flow. Now the particles which are in contact with the substrate or the particles in the stoss side, with unidirectional flow these particles are hit directly by the flow. If the flow comes and hit the stoss side of the ripples, so erosion occurs in the stoss side. The particles which are previously static in position, they are now starts moving with this flow. So they move most commonly as bed load or saltation along the stoss side of the ripples. After reaching the brink point, these ripples now stored in the crystal part of the ripple. Now when there is slow failure, that means the when these sediments are piled up and this pile is not sustain the weight or the angle is greater than the safety factor, then these sediments collapsed and deposited in the leeward side. So these sediments collapsed in the leeward side and deposited like this way. So my stoss side is eroded. So my previous stoss side, which is here, now it is eroded and formed a new stoss side and a new lee side. After that, again flow hits the stoss side. Again the same process occurs, that is erosion and transportation of sediments from the stoss side, and again deposition in the lee side. So ultimately the ripple is moving towards the down current direction. That is, erosion occurs from the stoss side and deposition occurs in the lee side. So this way, from this initial condition, after erosion the ripple formed like this, then again it is eroded and moved towards down current direction, and now it is oriented like that. Again it is moved in that, and finally to that. So you can clearly see that the stoss side and lee side gradually they are progressing towards the down current direction. So this way, in a repeated erosion from the stoss side and deposition in the lee side, a ripple mass or a ripple will move towards the down current direction. So basically ripple mark is not any static feature, that is once it is formed it will remain at its place. Particularly the current ripple or asymmetrical ripple, they progress or move forward with the flow along the flow direction. So you can clearly see that a ripple which is oriented like that at t1 time, with changing time erosion occurs in the stoss side, and at t2 time the stoss side becomes this, deposition occurs in the leeward side, that is indicated by the black colored portion, and now at t2 time the leeward side is like that. Now an important factor here is the erosion and deposition. Now for this figure you can see that only erosion occurs in the stoss side and deposition in the leeward side, that is all the erosion and deposition is restricted for the sediments which moved in contact with the substrate. But as I previously told, there are some sediments which are suspended in the flowing medium. So if those suspended particles starts deposit, so this process is going on, that means migration or moving forward of asymmetrical ripples, but net deposition from the suspended portion is less in amount, then these kinds of ripples are found. But when there is a significant contribution of uh, particles suspended particles which are suspended in the flowing medium, when they settled, then there is some erosion deposition component of the bed load sediments and some sediment components from the suspension. So instead of simply eroding the stoss side and depositing the lee side, due to the significant contribution of suspended load in the second type, here the ripples are vertically also stacking occurs. Vertical stacking also occurs. Uh, as you see in this case, that with significant contribution from the suspended load, that means deposition takes place frequently or often from the suspended loads, the ripples as well as the moving in the forward direction, they are also vertical stacking is also there. So it looks that one ripple is climbing over another. So these kinds of ripples are called as climbing ripples. Basically, for migration of ripple, there is erosion at stoss side, deposition at lee side. Very insignificant contribution of deposition from the suspended loads. So if we try to balance the erosion and deposition process, then for uh, ripple migration, my depositional rate, total depositional rate, that means, and for this total deposition rate, a significant factor or significant part is from the suspension load. The deposition is very less when ripple migrate for a unidirectional flow. But here for climbing ripples, deposition rate is very high, and simultaneously migration is also going on, but the deposition rate exceeds the rate of migration. So that is why ripples are slightly forwardly moved, but due to the increasing or far greater amount of deposition, it looks like the ripples are climbing over the previously formed ripples. Ripples climbed one after another. So that is why these kinds of ripples are known as climbing ripple. So that's all for today's class. Next day we'll discuss about the features formed by the ripple migration. Thank you.